All right. So today I will talk about integrated components for low noise amplification and isolation in a KITWPA architecture. So in this talk, I will go through the design of an on-chip duplexer and bias T and show you some preliminary measurements that we did in our lab with everything fully integrated together with the TUPA. So my name is Linus. I'm a PhD student in the group of Simone Gasparinetti. We call ourselves the 202Q lab. Basically, you see the full team there, apart from myself. But we do a lot of things regarding superconducting circuits. I primarily work together with these two people in the quantum enabling technology branch, and that is also the branch where we develop these kinetic inductance TUPAs. TUPAs are interesting devices. They show high gain and large instantaneous bandwidths, but still being close to the standard quantum limit of noise. And typically they are made from two different nonlinear mediums. It's either Josephson junctions or the kinetic inductance of thin films. There are pros and cons of both, but for example, I'm speaking about KITWPAs here. There are certain pros with those, and those are, for example, high power handling. They can stand quite high magnetic fields, and they typically work both at 10 millikelvin and 4 Kelvin. And that makes them sort of a natural competitor to semiconducting amplifiers. If you think about large-scale system where you are really concerned about high power dissipation. But one should also keep in mind that these type of amplifiers are also being developed in a rapid pace. So let's see who is winning the race in the end. But there's a lot of things, as we've been hearing in other talks during this meeting, that you can do to improve or exploit the full potential of TUPAs. And I think for the past year, there has been a lot of work in integrating more components, the biasing components on chip, which is of course a very important step if you want to make a compact device. For example, there has been a realization of this in a KITWPA architecture where you use a coupler for the pump injection and a bias T for biasing the DC for this three-way mixing KITWPA. There are also other works with JJ compatible fabrication processes that basically investigates, for example, reflectiveless filters, which are also really interesting components. So that's one part. Another part, which is also cool with TUPAs, you can have a simultaneous gain and isolation if you use, for example, other parametric processes by either using additional pump tones or by doing some clever combinations of passive devices and the TUPA itself. So that's also why we are interested in integrating these type of passive components in our device, and that's what the talk will be about. So just short about our material stack. So we use this inverted microstrip technology. We use a sapphire wafer where we deposit the nonlinear medium, which is the niobium titanium nitride. We isolate the niobium titanium nitride from the top niobium by growing some silicon nitride. And we use this kind of dispersion engineered transmission line with this fishbone structure, where we actually push the sort of feature size down quite a lot because we don't have that high kinetic inductance of our film, so it helps with the nonlinearity. To design these kind of devices, you really need to know your material parameters, and I mean, we really like this tool that we have. It's a high-frequency cryogenic probe station, which enables us to calibrate our scattering parameters right on the chip. So basically you have this kind of puck here where you place your chips, and you have this calibration substrate, and you can basically use this to extract your material parameters from test structures like this, like a simple inductor. You look at the reflection coefficient, and you can look at the imaginary parts, the omega L basically. And the same goes with the capacitive test structures. You have this parallel plate style structure, and you can extract your material parameters from that as well. You can also characterize more or less all your passive components in this. But now when we know these material parameters, we can start to design our circuits. So for the duplexer, we need both a low-pass filter end and a high-pass filter end. So the low-pass filter that you can see in blue here, it consists of 3 series inductors and 2 parallel plate capacitors. You can also see the high-pass filter here, which is 3 series capacitors with the shunt inductors, which are connected to ground with through dielectric vias. And as you can see, we get a very good agreement between the simulations that we made and the measurements we do with this probe station. And we operate our device in 3-way mixing, so we need a bias T, and a big part of the bias T is the DC blocking capacitor. It's a parallel plate capacitor, and this measurement is basically 2 DC blocking capacitors and a transmission line in between. So you can see the kind of broadband nature of this device here. And you can also measure your artificial transmission line. If you measure a short line like this, it's a bit easier to extract, for example, the impedance of it, but you can also measure the full-length device. So this is a bare device without the external circuitry. So this is the full device. It's a 7x7 centimeter chip. It's a 10 centimeter device. It's kind of hard to see, but it's meandered between these 2 biasing sections here. It consists of this duplexer here and the bias T here. There's also an additional component here, which is the AC blocking inductor with the decoupling capacitor there. And there you can also see the sort of SEM image of our artificial transmission line as well. So we cool down this device, and we just do some quick characterization, trace out the sort of phase matching condition by looking at the gain, and we do see gain. We can also see that we cut out parts of our band, which is of course not desired, but we can see that our passive component does not introduce any resonant features in our gain profile. When it comes to the true gain, it's maybe modest compared to other devices that have been realized, but we know that this device is not perfect. There are some improvements that we can make. We see some other maybe undesired features also, which is probably due to the quality of dielectric. You see this kind of power saturation effect, which is quite strong. So this is something that we're also looking into. Actually tied to the previous presentation, we had a work out a few weeks ago where we present a new thermal noise source that we built. It's based on nichrome film on niobium. And basically we can use this to calibrate our input line attenuation and our readout chain added noise. And it's a self-calibrating noise source. You only need a few nanowatt drive to get it to a couple of 100 millikelvin. And the heat up time is in the microsecond scale, quite similar to what we saw before, and the cool down time is milliseconds. And we don't see any particular heating with, you can use it at the mixing chamber, basically. So this is something we want to use to now also characterize our KITWPAs. So in summary, we have designed these passive components and they seem to perform as we want them to do. There's still some things to work on the actual core device, which is the KITWPA. But we know that there are a few things that we can improve. For example, we made a little mistake. So our line was 57 ohm unbiased. So that's something that we will adjust. Also, the bandwidth of the device, we can tailor that to be within the low pass filter of our duplexer. And we also want to characterize the noise with our new noise source. Please visit our group's website, and we actually have a postdoc position in our group for doing exactly this kind of development. So if you're interested, please talk to me or my PI Simone, and we're here the full week, so please reach out. Thank you.
We have time for a few questions.
Yeah, thank you for the great talk. I was wondering, you've simulated and measured the filters individually. Did you measure them together to be sure that their reactances didn't interfere and cause problems?
You can do that. We can only do 2-port measurements in this probe station. What you can see if you do measure it is that you don't have terminated you can't terminate the high-pass filter end if you measure the low-pass filter end, and the vice versa with the bias T. So you get this kind of standing modes because you have this huge transmission line which is not unbiased, but you can still see the cutoff frequency of those. So we don't see, I mean, they work perfectly, basically, or perfectly, but they do what they're supposed to do in a reasonably good way.
And you see that in simulation as well?
Yeah, yeah, we do that in simulation as well.
Thanks.
Any other questions?
So thanks for the talk. Many people use diplexers now, but if you look at the common port of diplexer, probably around the characteristic frequency, you'll see a lot of reflection. Don't you think that as you increase the gain, it will be limiting performance of the TUPA?
Basically, our stop band is well inside the high-pass filter, actually. So, and these are relatively, as long as you have your gain band inside the duplexer and the pump well in the high-pass filter pass band, it should be fine. And we haven't seen any strange things going on.
Okay, thanks.
Any other questions? Then I have a quick question. Do you have a sense as to what's causing your fairly high insertion loss on this? Or how does it compare to some of the other inverted microstrip structures?
Yeah, well, if I knew, I would have gotten rid of it. But we used aluminum oxide before, which was significantly worse. It was like the greatest filter, you could say, almost. So I'm not sure. I mean, yeah, you can clearly see these TLS saturation effects. There may be something that we can do. I mean, there are many works on this dielectric development, but I'm not sure what we can do. Probably many things, but.
Let's thank our speaker again.